Hello, I am Reuben Tate, and I'm here with Majid Farhadi, and we're both currently ACO PhD students at Georgia Tech. This work is with my advisor, Swati Gupta, and by Creston, Herold, and Greg Mohler, who are research scientists at GTRI. Today, we will be discussing the bridging of classical and quantum with SDP Initialized Warmstarts for QAOA. We first give a high-level overview. On the left, we have the classical realm of computing and optimization, and on the right, we have the quantum realm. In the classical setting, logical circuits can be used to move from one state to another. In the quantum setting, one works with quantum circuits, which uses a system of unitary transformations and measurements to move between superpositions of all possible states of the system. Theoretically, quantum algorithms are able to perform fast integer factorization via Shor's algorithm in quantum probabilistic polynomial time, which is provably better than any classical algorithm. Conversely, there are some problems, such as integer addition, which are better suited for classical computers. Our goal is to further strengthen the bridge between these two realms. For this talk, the bridge is in the form of a warm start that uses solutions from classical methods in order to give quantum methods a head start. Specifically, we will talk about initializing quantum approximate optimization algorithm with an SDP solution for Maxcut, which we now introduce.
Let's discuss a classical combinatorial optimization problem known as Maxcut, in which the input is a weighted undirected graph G, and the objective is to partition the vertices into two sets such that the total weight of the edges crossed by the cut be maximized. Let us see an example. Here we have a weighted 5-node graph depicted along with a feasible solution partitioning vertices into two sets of size 2 and 3. 5 edges crossing the cut with a total weight of 6. It turns out to be the optimal solution in this case. Maxcut is closely related to maximum satisfiability problem and numerous discrete optimization problems. One can represent a feasible solution by a mapping of vertices to plus and minus 1, corresponding to a vertex being in one side of the cut or another. The objective can be written as a quadratic function of such valuations of the vertices. The classical solution we propose for the warm start of QAOA is a low-rank semidefinite programming relaxation. This state-of-the-art classical relaxation of the problem maps vertices to not scalars, but vectors from a k-dimensional Euclidean space, while imposing unit distance constraints from the origin for vertices, as does the original +1 - 1 assignment. We utilize this method in particular for rank 2 and rank 3, where the vertices are assigned vectors from unit circle or Euclidean sphere. Now let's move to the quantum space. We briefed the quantum approximate optimization algorithm called QAOA, which is a hybrid algorithm introduced by Farhadi et al. In 2014, in which the state of quantum processor is controlled by variational parameters that are to be optimized by a classical computer. Here is the setup. We have an initial state S0, where each qubit is in the state plus get. A cost Hamiltonian H sub C and a mixing Hamiltonian H sub B are key operators defined by standard Pauli rotation matrices over n points of the edges, as well as individual qubits assigned to the vertices, as formulated below. An instance of QAOA with a circuit of depth P has two P parameters defining transformations using the cost and mixing Hamiltonians to be alternatively applied to the qubits. The final state of the algorithm, psi P, is sampled by a quantum measurement of the qubits, wherein the spin of the qubit determines the site the corresponding vertex falls into. The quantum expected value of the cut is denoted by F sub P and can be derived by applying the cost Hamiltonian to the quantum state. Let M sub P denote this expected value of the cut, the optimal choice of variational parameters. In other words, QAOA optimizes F sub P over all possible choices of gamma and beta and takes the maximum. Note that optimizing these variational parameters is not trivial, since the function to be optimized is not typically convex. Moreover, the optimization becomes increasingly difficult as the circuit depth P increases, due to the larger parameter space to be explored, as well as practical constraints of the quantum technology. There are various techniques and strategies when it comes to optimization. Our implementation in particular uses a gradient-based method called ADAM.
We are now ready to describe our Warmstart approach, which we call QAOA-Warm. The first step is to find a locally approximate solution to BMMCK for k equals 2 or 3. Here we have an example with k equals 3. We then perform a random rotation. Afterwards, we map the rotated solution to a separable unentangled state, which we then use as the initial state for QAOA. We'll now describe steps 2 and 3 in more detail. Classically, the value of the expected cut doesn't change with the global rotation of the solution. However, these rotations can change the quality of the cut when sampled in a quantum sense, which is why we add an additional rotation in order to mitigate a bad initialization. We have two different types of rotations. First, we have the vertex at top rotation. We pick a random vertex and effectively perform a global rotation that results in that vertex being rotated to the top. Next, we have random uniform rotations, where we randomly select a point on the surface of the sphere and rotate it to the top. Next in our pipeline, we describe the mapping from the rotated solution to the block sphere. We begin with k equals 3. Here is our rotated solution. Now, let's imagine that this is the block sphere. We look at the position of each vertex on the block sphere, interpret it as a quantum state, and take a tensor product, thus giving us an unentangled initial state S0. Now consider rank 2 solutions which lie on the circle. We embed the solution into the YZ plane of the block sphere. Then we again interpret the position of each vertex as a quantum state and take a tensor product. We now give some experimental results. For our experiments, we looked at randomly generated 12-node graphs. For both plots, the horizontal axis is the number of epochs done so far throughout the training process with variational parameters, and the vertical axis represents the percentage of the max cut achieved. The left plot corresponds to circuit depth p equals 1 and the right to p equals 3. We have 3 different colored regions, each corresponding to different variants of QAOA. The red region corresponds to vertex at top rotations with rank 3, the yellow region corresponds to uniform rotations with rank 3, and the blue region is the standard QAOA. Note that some regions overlap. On average, we see that QAOA-Warm in red and yellow outperforms standard QAOA in blue, and even more so with the lower circuit depth on the left. We can also compare rank 2 and rank 3 solutions as well. The setup for these plots are the same as before, but now the red and yellow regions are going to correspond to rank 2 and rank 3 solutions, respectively. Rank 2 solutions in red outperform the rank 3 solutions in yellow, which both outperform standard QAOA in blue. Next, we look at parameter landscapes. Let's consider QAOA-Warm on this 4-node graph with the following rank 3 solution. For each plot, the axes correspond to the variational parameters gamma1 and beta1, and the color corresponds to the expected percentage of the max cut we'd achieve with depth 1 QAOA. When no warm start is used, the landscape has various peaks and valleys, whereas when we do use a warm start, the landscape is flatter and more smoothed out, due to the fact that we are already starting with a good solution. Various trajectories of QAOA are overlaid on these plots with the black circle denoting the beginning and the white cross denoting the end of the run. We see that when we rotate vertex 1 to the top, the landscape is the flattest, with the trajectories ending on the line beta 1 equals 0. We also have the landscape where vertex 2 is rotated to the top, and uniform rotations as well. In general, the rotation used can have a significant effect on the landscape shape and on QAOA-Warm's behavior. In some cases, as shown here, the landscape flattens completely.
Little is known about theoretical performance guarantees of QAOA, especially in low-depth instances that are practical. At depth 1, for a special case of Maxcut on 3 regular graphs, Farhadi et al. Showed QAOA guarantees a 0.69 approximate optimality. In contrast, the full-rank classical relaxation of the problem allows a 0.878 approximation for Maxcut in the most general sense, thanks to the Gomez-Williamson algorithm. We note that performance of QAOA is non-decreasing with respect to the depth of the quantum circuit, and develop some theory to show why QAOA-Warm may start outperforming the original QAOA from the lowest depth. Note that QAOA begins with a half approximation guarantee due to its unentangled and unbiased initial state. We show our Warmstart can considerably improve the performance for low-depth circuits by preserving information from the classical solution, proving at the very depth 0, that is by quantum sampling of our initial state, the guarantee is 2/3 of the objective of any feasible solution to a rank 3 Bury-Montero. Similarly, 3/4 of the classical objective from any rank 2 Birol-Montero formulation is guaranteed by QAOA-Warm. One may have already observed the trade-off our algorithm provides with increasing performance of the initialization by decreasing the rank constraint for the classical stage. Birol, Montero, and Zhang showed even a two-dimensional relaxation thus performed significantly promising in practice, achieving near-optimal solutions for real-world and empirical instances. Moreover, non-convex optimization literature supports increased performance by Birol-Montero method by increasing the dimension of the embedding. Another confirmation on the Warmstarts leading to flatter landscape as well as improving the expected performance by QAOA is to note the Birol-Montero method can provide plausible embeddings of low rank. The further the vertices be pushed over the block sphere by the non-convex optimization objective, the better performance of the algorithm becomes. For extreme case of antipodal points on the sphere, our vertical top rotation preserves 100% of the classical objective. Such antipodal initializations of qubits are not enforced, but can occur and improve the performance of QAOA-Warm due to the Birol-Montero formulation. For example, a two-regular graph where QAOA is conjectured to guarantee only a factor 1 minus O of 1 over P optimality. We show the Birol-Montero relaxation searching for local optima in a non-convex landscape is guaranteed to find the rank 1 global optimum in dimensions as low as 3, allowing QAOA-Warm to be initiated with the optimal solution.
We now discuss some of the limitations of QAOA-Warm. Recall that as the circuit depth increases, standard QAOA is able to achieve the max cut in the limit. Does this theorem still hold for QAOA-Warm? Unfortunately, the answer is no. The proof by Farhadi et al. Relies on QAOA's asymptotic equivalence to the quantum adiabatic algorithm, which requires that the initial state is the ground state of the mixing Hamiltonian, which is typically not the case for QAOA-Warm. Even though we find an improvement for low-depth circuits, we find that certain initializations of QAOA-Warm can get stuck and not improve the quality of the max cut. To see this, we consider an example. Suppose we run QAOA-Warm on a graph consisting of a single unit weight edge with initial state plus minus. As we see in the diagram, this state is an optimal antipodal structure that lies on the x-axis. It turns out QAOA-Warm can only obtain 50% of the max cut regardless of the circuit depth or parameter choice. However, one might ask, what happens if we perturb the state while keeping the antipodal structure? By looking at these red points, we see that the perturbed solution can be characterized by the polar and azimuthal angles theta and phi of the first qubit. We can then create a plot where the theta and phi angles are the axes, and the color corresponds to M1, which is the expected value of the cut that we would get for depth 1 QAOA-Warm with optimal parameters. In the green area, we only get 50% of the max cut, whereas these crosses correspond to the problematic plus minus and minus plus eigenstates, which lie along the x-axis. However, these dark red regions are desirable. The vertical red bands correspond to points that lie along the YZ plane of the block sphere, which motivates our mapping of rank 2 solutions. In general, we're going to see that we want to avoid antipodal points that lie near the x-axis. We end with our conclusions and some open questions. First, QAOA-Warm appears to be well suited when working with low circuit depth and/or limited training time compared to standard QAOA. Additionally, QAOA-Warm drastically changes the shape of the parameter landscape, which has the potential to be further exploited. In terms of open questions, one might ask which graph classes or properties of graphs are well suited for QAOA-Warm. One might also wonder if our approach can be adapted for higher rank solutions beyond rank 2 or rank 3. Finally, recent approaches for QAOA consider using alternative mixers. In particular, a parallel study by Egger et al. Considers a different Warmstart approach with a custom mixer whose ground state is the Warmstart itself. Can we get better results by using a custom mixer that is better suited for QAOA-Warm? In the next 2 slides, we have our references and image credits. Feel free to view the video again after the talk to take a closer look. Thank you very much for your attention and for attending our talk. Our paper can be found at the following link or QR code. We appreciate any comments, questions, or suggestions you may have, in which case our contact information can be found below. We think merging of quantum and classical ideas is a very exciting topic to be further explored. So please don't hesitate to contact us to discuss any potential collaborations. Thanks again.